is Natan Andrei, thermodynamic in a split Hilbert spec, quantum impurity in an interacting line D system.
Okay, thank you very much. I would like to thank Mary Batchelor for inviting me to talk at this in honor of Rodney Baxter, a guiding star in our field who has impacted all of us. I'll talk about recent work done by two brilliant students, Pradeep Katel and Abhay Jakenov, and I'm going to discuss the thermodynamics of systems where the Hilbert space is split in a sense that I'm going to describe. So the system that I'm going to talk about are the Kondo impurity at the edge of a superconducting wire. Here is the, do you see my cursor?
Yes.
So this is a quantum spin half. And here we have a Kondo impurity at the edge of a spin chain. Here are the Hamiltonians. Oops, I did something and my screen has disappeared. Oh, okay. It's back. Here are the Hamiltonians. Here's the superconducting wire. It's a wire, so we have left-right moving electrons, and they interact via spin density, spin right interacting with density of spin left, opening a gap, and it's a spin singlet superconductor. With this is the operator that determines the decay. It's defined on an open system, and at the edge, there is a Kondo impurity, and it interacts with the system. The other system, it interacts with the superconducting wire. The other system I hope to have time to talk about is the XXX spin chain with, at the edge, a Kondo impurity, spin half Kondo impurity. So here is the outline of my talk. I will first describe the solution using a Bethe-Ansatz approach. I'll discuss the various phases. So the phases are going to be labeled by a parameter and renormalization group invariant parameter that I'm going to define. Here we have the Kondo phase, which takes place when the Kondo coupling J dominates the superconducting coupling. And we'll see that in this case, the impurity is screened by a many-body cloud, and all the excitations are built on one ground state, so we have just one tower of excitations. As we increase the strength of the superconducting coupling, and J now is of same order of G, we come to the bound state phase, or the YSR phase. J is of order G, and in this case, the impurity will be locally screened by a bound state that forms at the edge of the impurity. I will show now that the Hilbert space of excitations is built over two different ground states and forms two towers, which I'll call T1 and T2. In the case where the strength is still increased, we are still in the bound state phase, but now the impurity is unscreened, and there are three ground states on top of which we can build towers of excitations, T1, T2, T3. When the Kondo coupling is small compared to the superconducting coupling, another phase occurs, and this is called the local moment phase. Now the impurity cannot be screened on any energy scale, However, 3 towers are present built of 3 ground state. And a similar structure occurs in the spin chain. We have a Kondo phase. Here we have 2 bound state phases, a ferromagnetic bound mode phase and an anti-ferromagnetic bound mode phase, and again, a local moment phase where the impurity cannot be screened at all. So after I will discuss these phases, I will discuss how to calculate the free energy in each phase. We have to carry out a multi-tower summation. Namely, first we have to sum over one tower, then over another tower. And as a result, we'll get new effects which are not present if you have only a standard summation of one tower. So here what we just call this phenomena is split Hilbert space. So thermodynamics, partition function in a given phase is obtained by summing over the energies of the phase. So the partition function is a standard summation E minus beta n, and this defines the free energy. So the total free energy on a system with open boundary condition consists of 3 contributions. There is the bulk free energy, there is the boundary free energy, and there is the impurity free energy, which is the object of our interest. We are going to calculate the free energy using the Yang-Yang TBA approach. There is another approach, a quantum QTM approach, which would be interesting to do to compare results. For the experts, I'll make a comment. It's known that calculating the free energy from TBA open boundary condition often misses F boundary, and it needs to be calculated separately and taken care of. But it's not what we are doing here. It is not part of the impurity free energy which we are interested in, and which is obtained by subtracting the bulk and the boundary terms from the total free energy. So once we have obtained the impurity free energy, what we calculate is the impurity entropy, and this impurity entropy is the object that we are going to study in detail. It is in particular experimentally measurable in different setups. So there has been measured by the Fall group in other systems, 2018, or by Enslin and others, 2025. And just in case I don't finish, let me show the results. So here we have the entropy of the impurity in the different phases. So here is the Kondo phase, the entropy as a function of the temperature, and the usual Kondo effect, you can see at high temperature, I don't know why, at high temperature, we have the entropy being equal to log 2, namely the impurity is unscreened. As we lower the temperature, we move towards a zero entropy where the impurity is screened. That is essentially the Kondo effect, where as one lowers the temperature, the impurity is screened. The system goes from weak coupling to strong coupling. So this is just the usual Kondo effect, but what is interesting is that unlike the standard Kondo effect, which takes place with Fermi liquid and gapless excitation, here the Kondo effect occurs with gapped excitation. The spinons that carry out the screening of the Kondo impurity are gapped spinons. When we move to the YSR phase, we see very interesting curves which are non-monotonic. They still flow from weak coupling to strong coupling, but through a bump which occurs on the scale when the energy is of the order of the gap in the superconductor. Then there is another phase, YSR, where again the impurity is screened in the ground state. But here notice that we have a flow which log 2 goes back to log 2 from at high energy, high temperature flows through a non-monotonic flow, ends up at log 2. And the same in the local moment regime, where the impurity cannot be screened at all. There is still a small bump. Of course, the impurity cannot be screened, so we expect log 2, but there is a non-trivial bump that occurs. Similar behavior, but with opposite sign, occurs in the spin chain. Here is the Kondo effect, again, a flow from log 2, the weak coupling to strong coupling is a function of the temperature. When the impurity is screened, that is monotonic. And then there are the other phases, the ABM, namely antiferromagnetic bound mode, which is the analog of the YSR1 phase. And again, the ferromagnetic bound mode or the local moment bound mode. And they are all have very interesting structure, very non-monotonic. So let me explain how to carry out the calculations. So the solution, the beta ansatz solution, I'm going to talk now about the impurity attached to the superconducting wire. So the beta ansatz wave function consists of describes n electron in terms of their plane waves and their coefficient in the standard beta ansatz structure, moving on an open line and interact with the impurity. So the energy is given a sum of the momenta of the plane waves. Since it's linear, it requires a cutoff, which we call D, and the coupling constant G and J depend on the cutoff, and we have to carry out a standard renormalization, namely we take the cutoff to infinity, renormalize the coupling constant so that the physical quantities are held fixed and the theory does not depend on any details of cutoff anymore. The spin component, Sz, is given by the number n plus 1 over 2 minus m, where m is the number of downspin, and n plus 1 minus, sorry, not ups, n plus 1 over 2 minus m down, n plus 1 minus m downspins, upspins, sorry. The momenta Kj are obtained from the open beta ansatz Sklianin equations. And here is the structure of the beta ansatz equation. The momenta are given by the product of these factors. Lambda j are the spin momenta labeled by alpha. Alpha goes from 1 to m, m spin momenta. And they have to satisfy these equations. So the parameters that come into the equation, they have the standard form, so I don't have to explain. So B is the bulk parameter. B is essentially 1 over 2J. And D is written down here. It measures the relative strengths of J and G, and it's an RG invariant. It does not vary as the coupling constant, as the cutoff is sent to infinity. So it is the quantity that labels the different phases. It's given by square root of b squared minus 2b over c minus 1. So now the spectrum of the excitation is obtained by solving the Bethe-Ansatz equations, obtaining the momenta, calculating the various energies, and the different phases take place that I have discussed. So the bulk excitations of the spinons carry spin half, and mass, which is d sinh hyperbolic 1 over sinh hyperbolic pi b. And again, as I'm saying, when d goes, m is an RG invariant also. When d goes to infinity, b flows to 0 so that m is cutoff independent, and the theory has a gapped excitations. So as you see here, in the Kondo phase where we have only spinon, if this is the ground state, the excitations have a gap m, and then we can fill up the full spectrum of excitations by summing over the spinons, which are built over the ground state, which consists of n plus 1 over 2 real roots. And then the spinons are created by making holes and adding spins to fill out the full Hilbert space of excitations. So this is the Kondo phase where J dominates, it's larger than the coupling in the bulk. When we increase delta that measures the relative strengths between G and J, and it's now between half and 1, namely here, then a purely imaginary boundary root appears, which we'll call lambda delta. So its value is I times delta minus half, so it depends on delta. So it varies here. And now the bound state occurs, and it localizes a spin half at the position of the impurity and locally screens it. The bound state lies in the gap with energy E of delta is equal minus m sine pi delta. So delta is between half and 1. And then there is, so here is the plot. And you see, I can either fill the bound state, and I have then this energy of a bound state, which is lowered compared to the state U, where I choose not to fill the bound state. So as a result, I have two possible ground states, U and B, and then I have towers of excitations. Tau 1 here is built on U, on the ground state U, where the bound state is unfilled. And again, the ground state is lifted now by epsilon d, and then I have the tower of spinons built on top of it. Then I have tower tau 2, which is built on the ground state B, and again there is a gap, I fill it up with spinon. So tower tau 1 is built, let me repeat, on ground state U. U is made out of all real roots, and the bound state is filled. And this tower contains 3/4 of all excitations. Together, the excitations in tau 1 and tau 2 have to fill up the Hilbert space. But tower tau 1 contains 3/4 of all states, and tower tau 2, T2, contains only 1/4. When we keep increasing delta, and now delta is between 1 and 3/2, we are in this regime, new boundary strings appear, lambda super p delta L, and we can have in other words, I have delta of P equals to 1 and delta of P 2. What is interesting now, so I have three types of towers. I can have a tower T1, which built on U, only real roots, and it contains, so it's this one, it contains 2/3 of the states. T2 is built on B, where the real root is filled. It contains a quarter. And then T3 is built on P twiddle, where I fill the the fundamental bound state and the higher boundary strings, namely lambda of P equals to 1. It's this tower, and what the positions of the tower changes. Now, the lambda in this regime has negative energy, so tau 1 is, tau 2 is moved up, T1 is moved down, and when we have all three towers, the energies cancel, and again, tower T3 is moved down. So the fundamental boundary, lambda delta carries positive energy in this regime of delta. E delta is minus m sine pi delta. And if you look, so now I'm in this regime, and the relative positions of U and B has changed. And I have it, and the higher order boundary string lambda P equals to 1 has energy m sine delta, so it cancels, and therefore the energy of the string, and then again it's moved down. So T2 is moved up and T3 is moved down. Then when delta is larger than 3/2, namely the interaction in the wire is stronger than the condo, again, higher boundary strings appear. Hilbert space splits into three towers, similarly to what I described before. T1 built on U, only real roots. It contains a fraction of the states. This is a floor function which takes the lower integer part of 2 delta. So I have floor 2 delta plus 1 over 2 times floor 2 delta plus 1 of the states. Similarly, B, which has real roots and lambda delta. So we are here. And then we have T3 built on T twiddle. Now all those strings have zero energy, so none of them is lifted. And we have these three towers. Okay, now we want to calculate the thermodynamic beta ansatz. So we are using the approach of Yang and Yang, using the counting of all the states of the towers as I described them. So these are the standard beta ansatz. They emerge log eta n. Eta n are the Yang-Yang probability functions of sigma for string of length n whole over a density of sigma n. So log eta n is minus m over t cos hyperbolic. That is the driving term. And since we have only one flavor, it is at level 1. A sum over plus minus 1 because we have left-right movers. G, which is the standard operator, acting on log of 1 plus eta n plus v, and a boundary condition which tells us how the eta n's are going to behave in the limit where n goes to infinity. N really labels the spin of the string of length n. So from here, we can get limit value for high temperature and low temperature of n, which takes these values, which I'm going to use later on. So the point is that these TBA equations are the same at all phases, but I will see now that the expression for the free energy in terms of eta n depends on the phase. So in the Kondo phase, we have just one tower, and we carry out the summation, and we get the impurity and free energy is given by T over 4 integrated over log of 1 plus eta 1 over cosh pi lambda plus Vd. V is plus minus 1. That's a standard expression in the Kondo phase. If you have, for example, a standard Kondo model without where the electrons are just Fermi liquid, essentially you get only this Kondo phase and you get this type of expression, except that in the standard case, the theory is gapless and the gap moves down to 0. So as the energy is lowered, we are in the Kondo phase, so the S impurity decreases monotonically, as I mentioned, from log 2, where we are in the weak coupling, to 0 at strong coupling, and the impurity is screened by the spinons. So the same as in the standard Kondo case, the monotonic behavior persists, but it's interesting that in the usual Kondo, one can describe in terms of the G theorem, but the same physics occurs, although the G theorem does not apply because we have a gapped bulk. But we have similar critical behavior at low temperature as in the conventional Kondo problem. In the YSR phase, YSR1, where we are here, we have two towers. So now the partition function of the impurity, E beta F impurity, is the sum of the impurities in contributions in each tower. So here is the F in a tower, the free energy from tower 1, free energy from tower 2. And as a result, we are going to have the impurity entropy have this non-trivial monotonic structure. So why do we have a bump of order n? So that comes from this new type of summation where the impurity free energy is obtained by taking sum of two different structures, exponential structures, which we have now to take the log of and sum. So the impurity entropy, which is given by the derivative, now has a new structure emerging. It's of the form log z plus E delta over T E impurity of the tau 1 minus beta E delta over Z, where Z is given, is kind of the partition function of the impurity free energy. So it consists of two terms. There is a mixing term here, and there is an activation term. And we can calculate from the asymptotic values of the entropy at 0, at infinity, how this behaves. You see that the activation term vanishes for very low temperature and for very high temperature, but it peaks at temperatures, of order E delta, where the YSR bound state becomes thermally accessible. So we have a situation where we heat it up, suddenly new states which were before, they were not accessible, and now they were lifted, and now as the temperature reaches the right range, they are activated, and therefore a new type of excitations play a role, and S impurity has this bump. And then again, it is screened. So the impurity induces a mid-gap bound state whose thermal population produces a transient entropy bump.
Nathan, I'm afraid you don't have much time left.
Yeah, I was afraid of that. Okay, so do I have 3 minutes?
Well, at most.
Okay, so we have, again, the other phases, local moment, similar things occur. So let me summarize the first half of my talk. So in a gapped one-dimensional superconductor, the quantum impurity generates a rich phase diagram, unlike the Fermi liquid, where only Kondo phase exists. Here, the Kondo phase retains the same critical behavior as before, but the additional phases appear with distinct thermodynamics properties, and the phase structure is driven by the boundary roots, which reorganize the Hilbert space into excitation towers. And then, if I had time, I would talk about the spin chain, again, talk about various towers that occur in the different phases. And now, again, we have non-monotonic phases that are driven by new bound states that appear and reorganize and split the Hilbert space. So here is the final summary. So I've talked about this part. So the Heisenberg chain, again, with an edge impurity, generates a rich phase diagram driven by boundary roots which reorganize the Hilbert space into a excitations tower. And again, I have the activation energy being the energy of the boundary strings at the edge. And a general TBA framework for handling impurities that generate these bound modes needed to be devised. And what we showed then is that there is a unified approach to these and the thermodynamic signature and their experimental realization. And the outlook, we have many open questions. In particular, does the Hilbert space fragmentation that drives the impurity thermodynamics show up also in quantum dynamics and in transport? And does it show up in relaxation and non-equilibrium steady states, for example? And would such a mechanism also occur in higher dimensional or unconventional superconductors or in gapped insulator? We don't know. It would be very interesting to see. Very often happens that structures that occur in one dimension have the counterpart in a higher dimension, and fragmentation of Hilbert space would be an example. So thank you very much. Sorry, running over time.
Yeah, one quick question.
Natan, very interesting results you have. I have a technical question. You're talking about boundary strings and roots. Are they fundamentally different from the other roots and strings, or just qualitatively different?
No, they are fundamentally different. They are imaginary.
Okay.
Yes, they are pure imaginary, and they describe local bound states at the edge.
Yeah, understand. Thank you.
Yeah, so they are not the usual strings. The usual strings just couple they couple the holes into higher spins, but these are bound states at the edge of the impurity, and they are localized there, and then they have their own energy they can be either occupied or not, and that's how you get this type of towers, which splits the Hilbert space of excitations.
Thank you.
Let's thank the speaker.
Thank you.